So we're looking at the ratio and the root test for series. And we said with the ratio test, you take a special limit, n goes to infinity, of the absolute value of an plus 1 over an. If that special limit L is less than 1, then the series associated with that sequence converges absolutely. And if the limit is greater than 1, the series diverges. And if the limit is equal to 1, then you can't say anything about convergence or divergence. You just say the test is inconclusive. As far as the root test, you take a special limit, the nth root of the absolute value of an. If this limit is less than 1, the series converges absolutely. If the limit's bigger than 1, the series diverges, and if the limit equals 1, then the test is inconclusive. So we want to do some problems here. Determine if the series converges absolutely or diverges. Here's number 1. We're going to have the sum from 0 to infinity e to the n over n factorial. So notice how I have a factorial here. I'm going to use the ratio test. So here my an is e to the n over n factorial. And with the ratio test, I'm going to take a special limit, call it L. The limit as n goes to infinity, the absolute value of an plus 1 over an. Now that's the limit as n goes to infinity. So for an plus 1, I'm going to increase my value of n by 1. So rather than having e to the n, I'm going to have e to the n plus 1. And rather than having n factorial, I'm going to have n plus 1 factorial. Now if I decided to divide by an here, divide by an, it's the same as multiplying by its reciprocal. So rather than actually dividing by n, I'm going to multiply by the reciprocal of an. So I'm going to multiply by n factorial over e to the n. Now, I initially had absolute values, but I really don't need those absolute values because everything's positive, right? E to the n plus 1 is positive, n plus 1's factorial is positive, n factorial is positive, and e to the n is positive, all positive. So I can actually get rid of these absolute values, don't need them. So if I can write, there we go. We have the limit as n goes to infinity, e to the n plus 1 over the e to the n times n factorial over n plus 1 factorial. So here I've just aligned my e to the n plus 1 and my e to the n, my n factorial, and my n plus 1 factorial. Now I'm going to simplify. If I simplify e to the n plus 1 over e to the n, you basically subtract the power. So n plus 1 minus n, they're just going to give me 1. So I'm going to have e to the 1 power. And with the n factorial, that's what? N factorial on top, and on bottom, n plus 1 factorial is n plus 1, and then multiplying down from n, which would be n factorial. So basically here we're breaking up n factorial into n plus 1 times n factorial. So the n factorials cancel. So I end up with L being the limit. N goes to infinity, e over, so here on the bottom we have n plus 1. Now, e is just a constant, but n plus 1 is changing over time, right? It's getting bigger and bigger and bigger, so we have a constant over something that's getting bigger and bigger and bigger, so the whole term goes to 0. So since our special limit is 0, which is less than 1, then the series from 0 to infinity e to the n over n factorial converges absolutely. This is by our ratio test. This is by the ratio test. So ratio test you want to use anytime they're factorials for sure. Number 2. Let's say we have the sum from 0 to infinity -1 to the n plus 1, n to the n, over e to the n squared. So notice how I have so these powers with n, right? N to the n, e to the n squared. So I'll probably use the root test. Now maybe I'll put it up here. And with the root tests, our an is going to be, well, -1 to the n plus 1, n to the n over e to the n squared. So, root test, remember the root test. It's a special limit. As n goes to infinity, the nth root of the absolute value of an. That's going to be the limit as n goes to infinity. The nth root of the absolute value of an is -1 to the n plus 1, n to the n, and e to the n squared. So we have limit as n goes to infinity. Here the absolute values are going to kill off this alternating term that's either -1 or +1. It's just going to keep it 1 all the time, so you don't need to write that anymore. So we'll get rid of our absolute values and we'll get rid of that alternating -1 term. So we're going to have the limit as n goes to infinity, the nth root of n to the n over e to the n squared. So going down here, limit as n goes to infinity, we have the nth root of n squared over the nth root of e to the n squared. So that's just distributing the radical to the top and the bottom. So I'm going to have here the limit n goes to infinity, the nth root of n to the second power, that's just pulling that 2 out top. And we're going to rewrite this as fraction bar nth root. Let's see. I'm going to write this a little differently. All right, e to the n squared. And you see this nth root right here? We can write that as the 1 over n power. The nth root is the same thing as the 1 over nth power. So on top, I'm going to take the limit as n goes to infinity of the nth root of n. So pop the limit symbol inside of that parentheses squared. And on bottom, I'm going to have the limit. So the limit goes to the top and to the bottom. I'm going to have the limit n goes to infinity. E to the, so I'm going to take n squared times 1 over n. That's going to give me n squared over n. So on top, the limit as n goes to infinity of the nth root of n, this thing I'm circling in green, that's going to be 1. So that's a special limit, 1. You need to know 1 squared. On bottom, I have the limit as n goes to infinity. E to the, well, if you do n squared over n, that's going to be n. It looks like I have L is, well, on top I have 1, right? 1 squared is 1. And on bottom, I'm essentially going to infinity. So overall, this whole thing's going to 0, the limit's 0. So, since the limit, which is 0, is less than 1, then the series from 0 to infinity, -1 to the n plus 1, n to the n over e to the n squared, converges absolutely. Okay. What if we have something like this? Sum from 1 to infinity. How about n to the n over n factorial? Very interesting. So since I got a factorial here, I probably want to use the famous ratio test. So with the ratio test, here, of course, my an is n to the n over n factorial. With the ratio test, I want to take a special limit. N goes to infinity, absolute value of an plus 1 over an. So that's the special limit for the ratio test. So here I go. I got the limit as n goes to infinity. Now I really don't need these absolute values because everything's going to be positive, right? An plus 1 is going to be n plus 1 to the n plus 1 over n plus 1 factorial. So that's an plus 1. Then I have to divide, which means I'm going to actually multiply by the reciprocal of an. Reciprocal of an is n factorial over n to the n. So I could actually include these absolute values here, but I don't need them because everything's positive, so I can just drop those absolute values. So I'm going to have limit as n goes to infinity, n plus 1 to the n plus 1 over n to the n times n factorial over n plus 1 factorial. Going below here, we're going to have the limit n goes to infinity, n plus 1 to the n. Now I'm going to drop this power here, this n plus 1. I'm going to drop it by 1 by pulling off an n plus 1 to the 1, right? So this power, we take 1 off, so we have n plus 1 to the n, and then n plus 1 to the n. And on bottom here, I got n to the n. And then we have n factorial over, and this n plus 1 factorial we can write as n plus 1 times, multiplying down from n would be n factorial. So the n factorials cancel, and the n plus 1 on top and the n plus 1 on bottom and cancel. So we get the limit n goes to infinity, n plus 1 over n, all to the n. Right? Because they both have this kind of common n power that we can pull out. So I'm going to simplify this. I have the limit as n goes to infinity. So I'm going to take this n plus 1 over n in yellow right here. I'm going to break it up into two fractions. I'm going to break it up into n over n plus 1 over n. That's all raised to the nth power. We got the limit as n goes to infinity of, well here n over n is 1, so we got 1 plus 1 over n to the nth power. And this is a very famous limit, a very, very famous limit. This is a famous limit. Usually you just do this one in Calc 1. This is the famous limit E. That is the limit for E right there. All right, so our limit is E. So since our limit, which is E, is bigger than 1, since we have a limit that's bigger than 1, then this is by the ratio test. The series sum from 1 to infinity, n to the n over n factorial. Diverges. So here we're using the ratio test. All right, 4. Anything else? Okay, there's one. Sum from 0 to infinity, n to the 2n plus 1 to the n power. Now you see this big power of n right here? That power of n? Probably an indication you should use the root test. Oop, I lost it. Use the root test. So here our a sub n is n over 2n plus 1 to the n. And to do the root test, we're going to look at L. The limit as n goes to infinity, nth root of the absolute value of an. In other words, the limit n goes to infinity, the nth root of the absolute value of what? N over 2n plus 1 to the nth power. So going below, okay, we don't really need the absolute values, right? Because everything's positive. N is positive, 2n plus 1 is positive, the nth power is positive, everything's positive. We can drop the absolute value bars, you can take the limit, n goes to infinity, the nth root of n over 2n plus 1 to the n. So here the nth root cancels with the nth power, and we're going to have the limit n goes to infinity, n over 2n plus 1. So a simple way to take this limit is, notice you have a polynomial of degree 1 on top, a polynomial of degree 1 on bottom, so the limit's going to be the ratio of their leading coefficients. So the leading coefficient on top is 1, on bottom is 2, so it's going to be 1/2 is the limit. So since the limit is 1/2, which we know is less than 1, then this series from 0 to infinity, n over 2n plus 1 to the n converges absolutely. All right, there are a few